Hello, everyone. Thank you for coming. I can't believe you're all here today. That traffic, right? It took me forever to get here from the Venetian. But I'm glad you're all here. And I think we're all here today because we're building distributed applications. We want them to be reliable and highly available. We don't want our customers to be the first ones to let us know when something's wrong with our service. We want to be able to automatically detect and correct errors before customers notice downtime. So I'm Nari Haidapidyan. I'm a senior software engineer with AWS. And I'm going to be presenting with Calvin French-Owen, co-founder of Segment, who will come up later on. And I'm going to talk about some tools and best practices for monitoring and debugging your containerized applications. And Calvin will talk about how they're actually monitoring their ECS services. So microservices are a great way to build resilient and scalable applications. However, it also makes it really hard to monitor them because there are so many different interacting components. Now suddenly you have all of these services. You have load balancers, you have instances, clusters, tasks, and when something happens, you have to know where the failure is happening to be able to debug it. So you need visibility into all the different parts. Containers are also short-lived and transient in nature, which is great for development. However, it makes it hard to monitor them because the monitoring tools need to be able to automatically detect new containers as they come up and also grab logs before they go away. So let's say you have a mobile banking application. How do you know when it's healthy? Or how do you know when something's failing? And how do you figure out where it's failing? And when everything's running successfully, how do you know when you need to scale it so your customers don't notice a lag if there's a sudden spike in call volume? So these are some of the questions that you want to be able to answer to successfully run and operate a production distributed service. So let's talk about some of the key metrics that you want to track. So as we talked about, you want to have visibility into all the different parts of your application, starting from infrastructure and into the application level. So on the infrastructure level, you want to have visibility into your CPU and memory usage. You want to have visibility into your load balancers. So for example, you want to know if there are lots of requests being backed up and your application is not able to handle it. You also want to see disk space. So for example, are your logs eating up all of your disk space and not leaving enough for your application to run? Or things like database contention. And on the application layer, you want to see if you have error rates and which APIs are erroring out. Or you want to see request volumes per API, and you want to be able to break it down per customer. So you want to know if your customer, one of your customers is suddenly calling you a lot, so you can figure out why. You also want to see call latencies. So how long is each call taking? And is there a sudden spike or a drop? And that will give you insight into how your application is behaving. So fortunately, ECS is integrated by default with CloudWatch, which is a logging, metrics, dashboarding, and alarming system in AWS. So if you have the latest agent version on ECS, we automatically send CPU, memory, reservation, and utilization metrics to CloudWatch. Or you at least have to have agent version 1.4.0 or above. And this is what it looks like. So if you go to your ECS console, on the metrics tab, you can see CPU and memory, reservation, and utilization metrics. So for example, here you can see the utilization went up and then suddenly went down. And you will have to figure out what's going on. So what these metrics mean is the reservation metric is what you provide in your task definition when you say you want this many CPU and memory shares for your task. And the utilization metric shows how much you're actually using. We also break it down by service. So this will show you across your cluster all of your tasks, how much memory and CPU it's using. But what if you want to know, for example, how much service A is using compared to service B? So we also break it down by service. So if you go into the service tab, you will see metrics for that. And if you go into the CloudWatch console, you can actually see more metrics, and you can overlay them and graph them differently, or you can zoom into your graphs. So you just have more ways to look at your metrics and figure out what's happening with your service. So by default, ECS provides 1-minute granularity metrics. So what that means is that we collect metrics across all of your cluster instances multiple times per minute. But we only send it to CloudWatch once per minute. So if your memory suddenly spikes up for 10 seconds and then it goes down, you actually won't see it on your graphs. So what you might want to do, CloudWatch now provides put metric data APIs, and you can put metric and custom metric data and high resolution metrics into CloudWatch so you can track your application more accurately. One cool thing with CloudWatch is that you can create dashboards. So before, to see metrics from your different services like EC2, load balancers, ECS, you would have to go to different pages in CloudWatch and see the metrics on different pages. But that makes it really hard to correlate errors and failures. So if something's happening with your CPU utilization, you don't actually know if it's your load balancer causing problems or if it's your application. And with dashboards, you can put it all on one page, and you can easily correlate them. Another cool thing that you can do is you can actually overlay these graphs. So if you look at the CPU reservation and utilization metrics, the graph shows it to you on the same graph, so you can see if utilization is getting close to the reservation. It's much easier to see that rather than if they were on 2 separate graphs or on 2 separate pages. You can also monitor with our awesome partners like Datadog. So what Datadog provides you is if you install the agent on your ECS cluster, it automatically gives you CPU, memory, metrics, including usage, swap. You get I/O reads and writes. You get network metrics. You automatically get metrics around your pending, running, stopped tasks. And everything just starts showing up on your Datadog dashboard. Another partner that we have is Sysdig Cloud. What's really awesome with Sysdig is that you can see your application from an application level. So what that means is that, for example, with containers, if you see CPU and memory metrics, that's not very useful because it's not a one-to-one to an instance anymore. You might be running multiple containers on the same instance, so you don't see a breakdown. And with Sysdig, you can actually see a breakdown by task definition. So each task is using this much CPU and this much memory. And they also provide you application level metrics. So if you remember, we talked about some of the metrics that you want to track, like call volumes and error rates. And on the graph here, it shows you all of these metrics that Sysdig tracks automatically. You don't actually have to do anything. And you see top URLs, for example, or average and max request times, error rates. And so it makes it really easy for you to see what's going on in your application. So great, now you have metrics, and you see that your call volume went up, and you want to know which customer is causing that. Or your error rate spiked. Which API is it? How do you figure out what's going on? What you want to do is you want to have application logs. But it's awesome having microservices like we talked about, but what's really hard with them is now you have your application scattered across instances and containers. You don't want to have to SSH into every instance and grab logs and try to see where all the errors are happening across instances. What you want to have is you want all of your logs being forwarded to a logging framework or service, and just see all of your logs in one central place and be able to search and filter them there. So ECS supports multiple log drivers, and you can easily configure that in the task definition. And I'll show you how. So this is a screenshot of your task definition from the ECS console. And under the log configuration, you can see all the different log drivers that ECS currently supports. And it's really easy to configure. You just click on a log driver and provide the options to log in into your login framework and just forward your logs there. So let's talk about CloudWatch logs. You can forward your logs to CloudWatch with the AWSLogs Driver. So CloudWatch groups logs into log groups, And that just gives you a nice grouping where you can have access and retention metrics and search and filter metrics in one place where you just define it for that log group. And then for different applications, you would use different ones, potentially. Depends on your use case. So you have to provide the log group here in the AWS Logs group option. That's not created by the log driver for you. So you have to go into CloudWatch and create that log group. The next option is the region. So one thing that you can do is you can forward all of your logs from different regions into the same CloudWatch region. So you can see them in one place and just be able to search and filter and look at your logs in one region in CloudWatch. Or you can decide to send them from US West 2 to US West 2 in CloudWatch, or US East 1 to US East 1. So that's what you provide there. One really important option is the stream prefix. So what this is, if you don't provide anything, by default, it sends the stream to a container ID stream in your log group. So CloudWatch groups these logs by streams. So in the log group, as you can see here, it's just different streams coming into your log group. And it's not very useful because now all of a sudden you have all of these random IDs and you can't correlate which logs are coming from where. And for example, if you have an ECS service, and if your container goes down and then comes back up, now suddenly it's going to show up into a different stream prefix, and you can't really correlate it easily. So what you might want to do is just use the service name as the stream prefix, and then everything will just show up under the same stream. So now we have metrics and we have logs. It's great. Now we can track our application and know what's going on. However, you don't want to have someone sitting there and monitoring this 24/7. You want to be able to just be alarmed. You want to page yourself when something's wrong. Well, maybe you don't want to page yourself, but your company will thank you for it. So let's talk about how to do that. So in CloudWatch, for example, you want to alarm when your error rate is high. So you want to say, when I have 2 errors in 1 minute, page me. Well, you can do that. And what you do is you have to create a metric filter in CloudWatch logs. What that is just it's a filter, or it's a pattern or a word that you provide in your log group. And you say, here, for example, I'm looking for access denied. And if this happens n times per minute, please alarm me. I want to know about it. That's just configured in the CloudWatch logs console. You can also auto-scale your service and instances using alarms. So what that is you can define memory and CPU alarms in CloudWatch. So you say, if my memory went up to 75% utilization, please alarm me and also scale my service by this many tasks. So now I have more services available, more instances of my service, and the load is more balanced. You can provide this alarm to auto-scaling groups as well, and it'll launch a new instance into your auto-scaling group into your cluster. So now we have metrics, we have logs, alarms. Our service is running great in production. What do we do if we have a new deployment and we get paged because it's failing? So your service is not launching tasks. Or your tasks go into pending and then they disappear. They never go into running. How do we figure out what's wrong? So the first thing that you want to do when there's something wrong with your service is you go to the service tab in the ECS console and look under the events. Here you can see that the service was not able to launch a task because there was not enough memory available on your instances. So if you had that alarm that automatically launches a new instance into your cluster, your service would be successful. But at least you can debug it this way. And for task failures, if your tasks go from pending to stopped, you can go into the stopped tab under tasks. And we provide you with more details around why the task stopped. So here you can see that the last status was stopped, and the stopped reason was that the essential container and task exited. That means there's something wrong with the container. And if you scroll down, under containers, you can see more details around why the container stopped. So for example, the image was not able to get pulled from Docker Hub or ECR, and that's why your container was not able to start. So this is great. You can see this on the console, but what if you want to alarm on it, or you want to search and filter in one place and not have to go into the console every time there's something wrong? Well, you can do that too. What you need to do is just have the CloudWatch logs agent on your ECS instances. And one easy way to install these agents is just do it in the user data in the EC2 launch configuration. So every time a new instance comes up, it automatically launches the agent. So you don't have to go and install it every time you have a new instance. And then all you have to do is just configure which logs you want forwarded to CloudWatch. So you can have instance, you can have Docker daemon, you can have ECS agent and ECS init logs. And these logs will have more details around your task failures. And this is what it will look like in CloudWatch. Once you have that configured, it just has your instance, Docker, and ECS logs. So now, let's say we're going back to our mobile banking application. Everything's running successfully. But in the beginning of the month, you notice a huge call spike. What's going on? So you have your application logs. So you go look into them, and you see that people are looking at their pay stubs. They want to see if they got paged. Not paged, paid. That's a better one. So now you know that you need to pre-scale so your customers don't notice a lag when they're looking at their pay stubs. However, you're generating all of this data, all of these billions of logs and lines, and you don't want to have to manually sort through them. That's very tiring, and it's not easy to do, and you might not notice trends. What you can do is you can use search and analytics tools. So with CloudWatch, you can forward your logs to Lambda, Kinesis, and to other applications from there, or you can even use Elasticsearch, which is a search and filtering tool, and you can integrate it with Kibana, which is a visualization tool that will show you all of these logs in nice graphs so you can easily see what's going on, and you can detect trends from there. You can also do this with our partners, the ones that we talked about, or some other partners that we have, as they provide lots of analytics and search and filter tools as well. So Amazon actually hosts Elasticsearch. You don't have to manage it yourself. So it's just the open source tool, but we host it on AWS. And from CloudWatch logs, you just go into your log group and you say, forward my logs to Elasticsearch. And I can search and filter from there. So what did we learn today? For the health of your application, it's critical that you have metrics and logs, and you want to have visibility into all the different layers, starting from your infrastructure into your application. You want to have application logs and alarms. You also want to utilize all of this data that your application is generating to detect trends, anomalies, and patterns. And there are different tools that you can use for that. Thank you. I'm going to hand it over to Calvin to talk about how they're using ECS and Segment.
Cool. Is this mic on? Everyone hear me? Cool. Hi, everyone. I'm Calvin, co-founder and CTO of Segment. And for today's talk, I was actually inspired by this great Brendan Gregg blog post, where he talks about basically his first 60 seconds whenever he logs on to a Linux server. And it's not prescriptive anyway. It's not telling you what you should do, but it shares a lot of the techniques that someone who's a real pro uses. And I wanted to take that same idea of sharing like a tool set from someone who's really experienced to answer the question, hey, if it's 2 a.m., I'm getting paged, what do I do? And share some of the tools that we've found really, really useful at Segment over the course of our 2.5-year history with ECS. Now, can I get a quick show of hands? How many of you are using ECS in production today? Okay, it looks like about 30% or so. That's awesome. At Segment, we are currently processing around 140 billion events every month. These are just tracking data that comes in via various web pages for thousands of customers on different websites across the web. We're currently processing about 160,000 events through our Kafka and streaming infrastructure at peak. And to do that, we're powered by 16,000 containers running across 350 ECS services. And so by now, we've actually gotten to the point where we have a fair amount of sophistication and a fair amount of variety in terms of what services we're actually running. So when something goes wrong, there's a lot of places where you can look. And in particular, I find there's kind of three major findings or major ideas that we've had when something goes wrong and you're on call. The first is that you want to build your mental model, just understand what's going on. The second is that you actually want to dig in to the problems that you're finding. Look at an individual process level or service level or host level and really understand where things are going wrong. And the third is, if possible, you want to solve the problem. And for that, we found a variety of ways to really just lean into the cloud. And I'll talk more about that shortly. But first, building your mental model. If you're encountering a production issue, the first thing that you want to be able to understand, whether it's a service you wrote, or a service you didn't write, or a service that maybe you've never even seen before, but somehow you're getting paged for, you want to know, how does this system fit together? What's going on? How is it configured? The second piece is you want to know, okay, given that broad system, how does this individual service fit within that? How is it configured? And then finally, what even should I be looking at? What are the major areas? So to understand how the system fits together, we actually wrote our own tool which sits atop various ECS APIs, and we call it Specs. It's open source and put out there for you today, so you can just grab it off GitHub or Docker Hub and just spin up the Docker container to run as you choose. What Specs gives you is a dashboard similar to what you'd find with the ECS dashboard, but instead, it's maybe a little bit more user-friendly. It contains a list of all of the services that you're running split up under each individual cluster. And for each service, it's great because you don't need an AWS account if you're one of the members of that dev team who isn't dealing as much with the core infrastructure. And second, you don't have to page through hundreds or thousands potentially pages when you're looking for particular services in your account. For each spec service, you can actually click on it and pull out a tab and understand how that service itself is configured, everything down from the CLI, or the command line arguments, to the environment variables. And for each one, you can understand how many copies are running. You can see the list of events that Nare mentioned earlier, and you can actually drill down into individual tasks, which link back to the actual Amazon dashboard if you'd like to get a sense of what individual tasks are running. Like I said, you can actually just grab this today, Docker run segment specs, or you can check it out on GitHub if you'd like. It basically requires one IAM role that's able to read from the ECS API, and then a handful of permissions, and you're kind of off to the races. And you can run this as an internal tool or elsewhere, depending on what you need. So if I'm looking to understand how my service is configured, I can use specs. But a lot of times that configuration changes over time. And actually, in my experience on call, the single biggest question that I end up asking whenever something goes wrong is, what changed recently? And so for that, we use Terraform. Now, for those of you who are unfamiliar, Terraform gives you this configuration language that's fairly similar to CloudFormation. It allows you to build individual modules to boot up a bunch of different pieces of infrastructure underneath. So we use Terraform to create all of our services. Here you can see this is actually the Terraform for specs in kind of a meta way. And what this does under the hood is actually generate this giant dependency graph of load balancers, services, auto-scaling rules, network security groups, IAM roles. It creates it all for you, but as a developer, you don't even have to think about it. You get this like 15-line configuration file, and then you can say, hey, Terraform, I want you to create my service for me. Just let me give you the image in the version that I want to run. And in terms of actually interacting with that, we keep Terraform all entirely version controlled. So here you can see my teammate, Jeremy, actually swapping out the usage of our various ECS instances. We're testing out some of the new C5 instances. The beauty of this is it actually just requires a 2-line change in order for us to actually start testing this new instance type in production. We can test it in stage first, which we keep an environment for, then roll it out to production. And it requires no manual scripts on our side, no craziness in terms of reprovisioning, just this 2-line change, and suddenly we're able to start changing vast parts of our infrastructure without any work. To actually execute these plans, you end up merging into GitHub, into master, and then you run Terraform apply through Terraform Enterprise, which is a HashiCorp product. The reason we decided to use Terraform Enterprise is so that we can actually see when changes were made and audit them. So if, for instance, we change to a new instance type or deploy a new version of the service, we know exactly when that change went out, who confirmed and applied it, and why that change was made. And in general, having this version history, along with a set of commit messages associated with it, has allowed us to dig back over months or even years to understand why a given change was made. And finally, what even should I be looking at? We understand our system at a high level. We understand how little pieces of it are configured. For that, we use Amazon's CloudWatch and Datadog, which I'll actually touch on a little bit later in this talk as well. And for Datadog, this is kind of our central reporting interface for all of our metrics. Each individual service gets its own dashboard. That dashboard combines CloudWatch metrics along with StatsD metrics that we're actually piping into the service itself. And we're using it to monitor both the AWS resources, things like RDS instances, CloudWatch logs, S3 buckets, et cetera, and tie those metrics with our actual application-specific metrics, which are coming from StatsD. And what's great about this tool is actually it will also ping into things like Slack. So if you have a member of your team, in this case Julian, who's on call, you can get kind of this conversation going where people are responding to alerts in real time, but able to discuss them in the tool they're already using, Slack. Okay, so we've got our mental model all set up now. The next step is we actually have to dig in and understand what's going on with each of these services. And for that, there are basically 3 pieces that we need. We need to make sure that we have good stats, where the service is reporting what it's actually doing, where it's spending time. We need to have good logging to understand at a more human-readable level kind of the progression or execution of various events that the service is completing. And finally, we need to have a good sense of the tracing for the service. Where is it actually spending time right now? For the first one, we use CloudWatch and a combination of StatsD, in particular this open source program written by Stripe called Veneur. Veneur is essentially a StatsD sync that's fully compatible with the Datadog format. So if you're already recording StatsD metrics from your program, you can simply run Veneur on the machine and then pass in its address as configuration. How this looks for us is we run Veneur via systemd. Basically, we just run this simple Go binary. We don't have to do any sort of interpretation or compiling or anything on the box. And for our programs, we'll actually specify and say, hey, I want to pass in this StatsD or this Datadog address as the address of the Veneur server when proxied through the Docker daemon. And kind of the beauty that this gives us is it allows each of our individual services to send their stats and metrics to Veneur, or be passively collected by the Datadog agent, which is recording metrics on the host. And from there, we're actually able to combine them with all of these metrics that we're getting absolutely for free for things like load balancers, RDS, et cetera, from CloudWatch, and combine those in Datadog. What it means is that if I'm a developer, I can record really custom metrics that are important to my particular program's execution. But I can also combine it with all of the things that AWS automatically gives me. And if I want to, I can grab things like not only system load off the agents, but any of the AWS automatically reported metrics. So we've got stats, CloudWatch, StatsD, Datadog. The second piece is logging. And for that, we actually use a reasonably complicated setup of CloudWatch, this program called ECS logs, and CW logs. Now, for a high-level look at how our logging works. Basically, and I think this is essentially how it worked maybe 3 or 4 months ago. We have a bunch of containers, all of which are logging via standard out. Those containers send their logs directly to the Docker daemon, which is configured to send to journald. Journald itself is something that we prefer because it allows us to jump onto an instance and actually look at both the system logs, which are piping to journald, as well as our individual Docker logs. We're not quite at the point of sophistication where jumping onto an instance is something that's never useful. So for us, it's helpful to have all of those logs be accessible via a common interface. From there, we actually pipe journald data out into this proxy, this adapter called ECS logs. And ECS logs is just a Go binary, which basically tails journald, and it looks for individual journald entries, which are tagged with a container ID for ECS logs. From there, it will send those to any of the supported adapters, Loggly, CloudWatch, LogDNA, you name it, and it allows us to disintermediate the actual logging step of the program that the application is doing from the places where the logs are actually used and read. And this worked great for a while, but after some time, we actually ran into a little bit of a problem with journald. And in particular, it comes down to how journald handles rate limits for individual processes and individual containers. In particular, you can specify in your journald file a particular rate limit. In this case, we can say, hey, every 200,000 log lines that happen once a minute, stop logging after that. You're done. But what happens is journald actually treats that limit on a per process basis. And in terms of logging, it's all coming from the Docker daemon. So what happens is you have one really hot container, which is just spewing logs for some reason. Maybe it's crashing, maybe it's trying to connect to a database that's not there, whatever it is. And that actually uses up the overall rate limit for all of your containers on ECS. Not great. So what we did is we introduced something that's effectively a syslog proxy, or a syslog server, which sits in front of journald. We configured the Docker daemon to forward its logs to what we call this rate-limiting log proxy. It's maybe not the most imaginative name, but it is accurate. And what this does is it actually treats each container's individual stream differently. So what it can do is it can rate limit only a single container at a time based upon the tags that are being passed from the Docker daemon. In addition, we said, okay, we still really like CloudWatch. Why don't we make it easier to use CloudWatch logs? And in particular, we built this tool called CW logs, which you can see up here. What this does is it groups our individual log streams based upon the ECS service. So we create a group still per service, and then we have a list of tasks which we can access all via the command line. If we'd like to, we can fetch logs for all of the tasks within that service. So here we're grabbing all of the logs for Dynamo Writer. And you can see they're nicely output, and they're prefixed with kind of a shorter version of each of their individual task ARNs. But if we'd like, we can only look at a single stream as well by passing this -t flag, which actually allows us to grab only a single task's output. Here we can see for this given container exactly what it's writing. And additionally, we can also output this data as JSON. So if we'd like to, we could pass it to JQ or some other formatter if we'd like to programmatically access those logs, or if we'd like to programmatically filter them somehow. Like I said at the beginning of the talk, all of these pieces are open source and up on GitHub today. We use our ECS logs proxy to actually fan out that Docker data and send it, fan out that log data and send it to CloudWatch, Loggly, LogDNA, wherever we need it to go. We use our Go and JavaScript libraries to actually create those logs in a way that's machine readable and nicely formatted. We use our rate limiting log proxy, which you can just download and run as a Docker container, which will automatically limit for logs, which will automatically limit containers that are sent to journal D. And finally, we use CWLogs as our sort of Swiss Army knife CLI for accessing these logs. And I'd say in general, with CWLogs and CLIs in general, no matter how fancy or nice your UI gets, as programmers, we've kind of found no better substitute for dealing with a large amount of log data than your command line tools. Stuff like grep, sed, awk, whatever it is. Being able to use those logs from the command line is immensely powerful, but getting the cheap audit logging and cheap tailing cases from CloudWatch is just a great combination in terms of offloading the infrastructure that we have to manage. So finally, in terms of tracing, the two tools that we use most often here are BCC and pprof server. Now, BCC itself stands for BPF Compiler Collection, and BPF stands for Berkeley Packet Filter. It's a little bit of this weirdly named kernel feature which was recently added to recent Ubuntu kernels and recent Linux kernels, where you can think of it as almost a VM that works inside the kernel. So if you'd like to, you can actually instrument and understand what various syscalls are being made. You can understand disk usage. You can understand a lot of parts of how your program is running passively without you needing to add any instrumentation to your program. And in particular, these tools are all kind of put up at this IOVisor BCC GitHub repo where they kind of come pre-packaged. So as long as you download them and run them on your machine, you don't have to do anything. You just get these metrics for free to understand what's going on. So as a quick example, we can see here from one of our Kafka boxes, which is basically a bunch of Java processes which are writing to a rated XFS drive. We can see that here, all of these Kafka processes are doing a ton of writes at any given time, and we can know exactly on a per process basis kind of how much time is spent writing, how much time is spent reading, exactly what that process is doing. Even though we didn't write any part of Kafka, we haven't instrumented it in any way, we're just using these metrics that are given to us for free by the kernel. Similarly, we can actually check the read time and write time for this XFS drive and understand kind of a histogram showing the distribution of how long it's actually taking us to read or write. If for some reason we start shifting this write load down into maybe bigger and bigger amounts of time, we can understand that, okay, we're actually I/O or disk bound, and it's not a fault of the program itself. On the theme of tracing without having to add anything to your code, the other big tool that we use often at Segment is what we call pprof server. And this is actually one of my favorite tools that my coworker Ashil wrote that I've been using over the past 2 months or so. Now, for those of you who use Go, you might already be familiar with pprof. It's essentially this library that you can import. You just add this kind of single line to your Go program saying, hey, I want to listen on this server and expose these metrics. And it'll actually automatically give you stuff like profiling, heap dumps of where various Go routines are. It'll tell you where various memory is being spent, whether there's contention on various mutexes, etc. And so we thought, wow, there's this amazing tool which is just given to you basically out of the box. You add a single line to your Go program. What if we made it easy for developers to actually access that data in real time for a production account? And that's what pprof server does. Basically, each service, when it comes up, registers itself within console, which we use as kind of our shared service discovery platform. And when it comes up in console, we'll expose the URL as well as a set of links that you can just click through. And it can tell you in real time exactly where time in your program is being spent. It generates this nice SVG graphic telling you, hey, you've got a certain amount of time being spent here. Of that, there's maybe 1 second being sent here, or 1 millisecond being sent here. It allows you to get really fine-grained observability into what exactly your program is doing. Like I said earlier, you can get heap dumps for it, understand where your memory is being allocated, and this tool has essentially been invaluable for us when it comes to hunting down contention of various locks or mutexes, where one single bottleneck of your program is essentially slowing everything down. Just like specs, just like the log proxy, you can run this yourself. The only thing that you need to pass it is the registry of the console address, and from there, you're off to the races. You just connect to this service, and you can actually start understanding where your programs are spending time in real time. So those were the three of really digging in and understanding what's going on with an individual program. We've got our host level metrics that we're connecting from Datadog. We've got our individual process metrics that we're collecting from statsd. We've got our automatically defined kernel metrics that we're getting from BCC. We've got our Golang metrics that we're getting from pprof. The last step is actually fixing the problem. And the best luck we've had there at Segment is really leaning into the cloud. Now, what do I mean by that? Well, Adrian Cockcroft has this really famous saying that you want to treat your servers like cattle and not pets, right? You want to be able to just take one down and make sure that another can come up in its place. There's nothing really special about it. And in our case, that comes down to a few big tenets. But I'd say the biggest ones by far are, one, kind of reproducible machine images. The ability to boot up AMIs and be 100% confident that your machine is going to have everything it needs on it pre-baked. And it won't have to go out to the network to grab a bunch of resources. It won't have to install a bunch of things when it comes up. That AMI has everything it needs. For that, we use Packer, which is another HashiCorp product. And what it lets us do is actually provision that machine via JSON config file, and then it's run via systemd. Autocorrect kind of got me here. And the second of those is actually using out-of-the-box auto-scaling. We want to make sure that for every instance, it's part of an auto-scaling group. If one machine goes bad, we don't care, we just terminate that machine, and we're confident that other containers will come up with that machine, another machine will boot in its place. It kind of takes care of all the hassle for us. What this actually looks like in practice is we keep a GitHub repo that we call EC2 images. And here you can see all of the different AMIs that we're actually using, depending on which cluster we're booting in. And the reason we pick different AMIs per cluster is actually because some clusters have slightly different needs. Some of them are running stateless services, which is kind of this big one that we call Megapool. It's just sort of the general place where if you're booting a service, you put your service definition. Some of them are running Kafka with like really heavy write workloads where they're totally stateful. Some of them are maybe somewhere in between, where maybe they're running one-off tasks, whatever it is. If you look at the Packer file, what this does is it actually provides you a programmatic way as well to provision your service. So you can say, hey, I want to give this service, create this instance with this set of configuration. I want to create it with this set of scripts, and it will actually boot up an instance for you, run all of those scripts, create the AMI out of it, and then output that little AMI ID that you can use elsewhere. When we look at what these scripts look like, we basically keep a single one per each of the programs that are automatically installed on the machine, and we just run through them sequentially. That way we know when the instance actually boots up, we're not getting some other version of a service that we specified or some other piece of configuration. We're getting exactly what we asked for when we built the image. Reproducible builds are one thing. The other thing is having auto-scaling everywhere. As I mentioned before, auto-scaling for us comes by default with every service. When you specify that little piece of Terraform configuration, you automatically get auto-scaling rules in response to CPU and memory. And in places where we don't have that, things like Dynamo, we put it into place to make sure that we're not having production incidents all the time. And I'd say the general rule that we've kind of come to accept over the course of building these systems is that if you don't have autoscaling in place, you're really not ready for prod. Autoscaling allows you as the developer to not even really think about stuff like how much CPU or memory your program is using, because you can be assured that if, say, something happens where we get a big spike in terms of load, you'll just create more and more of that set of programs, and you don't have to worry at all because your service will scale horizontally. What this looks like concretely is we keep rules around for scaling in regards to CPU and memory. If CPU goes up by a certain percentage, scale up. If memory goes up by a certain percentage, scale up. In general, what we found is this works really well so long as you don't have contention. As I mentioned earlier, if you have some place where you have a shared mutex or like some place where you're not actually taking full advantage of the CPU, these rules won't work for you, so it's worth doing a bunch of those other things first before you actually start scaling via CPU. Though we've also talked about things like scaling in response to queue depth, request load, etc. So in closing, a few of the lessons we've learned. You want to build tools to surface the actual information or actionable information first. If you got a bunch of noise that's sitting around or a bunch of alerts that aren't really actionable or aren't really doing anything, you're just causing more of this kind of sea of information to crop up, which people then have to wade through and understand. Autoscaling is a huge win. Before, we would manually scale up or over provision, and it'd last us about 6 months until we kind of hit our next inflection point, and then we have to scale up again. By autoscaling, we've been able to boot more services earlier because we don't have to worry about a new service failing to scale and then bringing down the entire pipeline. On that note, give developers alerting and scaling policies out of the box. Don't make it so you have to pass a bunch of configuration every time you want to boot a new service. Just make sane defaults there for everyone. And from there, you can actually allow customizable tweaks. And then finally, passive tools are some of the easiest that we found to build adoption around. If you don't have to import other libraries, you don't have to add a bunch of configuration, you don't have to do things like add tracing points to all of your code. If you get all of that for free from tools like BCC, or tools like Specs, or tools like our logging configuration, then 9 times out of 10, you're just going to do the easy thing, which is also the right thing. And you're going to use these tools out of the box and make sure that they actually just work for you. And with that, I'd like to thank you for your time, and thank you, Nare. Thanks.